Hallo, أوزمار مشنوی؟ أوزمار مشنوی؟
بله میشنم.
بله میشنم استاد.
Yes, sir, we do.
Okay, good. سلام علیکم. بسم الله الرحمن الرحیم. امروز درس خود شروع میکنیم. So we have concluded the introduction to statistics and then a brief introduction to the probability. We will be proceeding toward regression analysis. Before going to the regression analysis, so all the time people, they are just misunderstanding the difference between regression analysis and difference between correlation. So first of all, we will be just paying attention right now to actually what's correlation. If you remember, we had a practice that we populated, we created some charts there, and then we examined it was part of EDA, and we examined the correlation there. In one of the charts, there was a positive correlation, and in another chart, it was just no correlation recorded. So this is how a perfect positive correlation would look like. So what does it mean? It means if the values on x-axis is increasing, accordingly, a value on y-axis is also increasing. That's called positive correlation. Zero correlation, that you cannot define how. If x is increasing, y is increasing or not. Here, x increased. Look, this here, x increased, while y is still in this level. Here, for example, x is not in a very lower level of increment, but y is increased too much. So you cannot define, is there any correlation between these two or not? Or difficult to define that. So, for example, this is one um, variable and this is another variable. And this is perfect negative correlation. What does it mean, negative correlation? It means if x is increasing, y is accordingly decreased, vice versa. Look at this. X is now increased to this level, yeah? Y is increased. Sorry, y is decreased. So this is the lowest level of y, and this is the highest level of x. But this is the lowest level of x, while this is the highest level of y. So if x increases, y is decreased, or y is increased, x is decreased. This is how a perfect negative correlation means. So correlation measures the strength and direction of a linear relationship between two variables. The correlation coefficient, as R that we are saying, is ranged from -1 to 1. What does it mean? This R coefficient of correlation. If it is equal to 1, it means it's a perfect positive correlation. So in this case, if R is equal to 0, there is no linear correlation. Look, this is no linear correlation existing in this chart. But one of the things that you have to pay attention to that we will be later on understanding that we are talking right now about the linear correlation. So it means from this chart, you understand that there is no linear correlation existing. But maybe then we later on understand some other techniques to examine that, and maybe there are some relations existing, but those relations are not linear relations. So this is also, please pay attention to that. And when R is equal to -1, it means there is a perfect negative correlation in this case. This is how it works. Now, just assume that we have a X date of 10, 10, 20, 30, 40, 50, for example. And then we have an axis of Y, which is 15, 25, 35, 45, like that. And these are two axes, and we want to calculate the correlation coefficient between these two ones and understand how, without even visualizing that, the data visualize with even if you're visualizing it, for example, in this case, visualizing actually helps us to define the correlation. But even in this such cases, you're thinking that maybe there is no correlation, but still there is something. There is something. In order to define that properly, understand how much is that coefficient actually, you have to define a correlation matrix. And this is the function from NumPy that you can use. And you can say that NumPy dot correlation coefficient. You want to find the correlation coefficient between X and Y. And this is how the correlation coefficient will be the correlation matrix, which is this one. This is the coefficient. 0 and 1, between 0 and 1, yeah? So now you have to print that one, and now we will see that this is correlation coefficient is actually, in this case, in our case, that this is 1. It means there is a direct positive uh, uh, correlation exists. So this is this case, see? What does it mean? It means X is increasing 10, 20, 30, 40, 50. Y is 15, 25, 30. Y is also increasing. See? So X is increasing, Y is increasing. So this is how this positive correlations exists there. This is how you have to understand the correlation and the positivity and negativity of the correlations between these according to the coefficients of these charts axes. Now coming to the interpretation, a positive indicates that as X increases, Y tends to increase. A negative coefficient suggests that as X increases, Y tends to decrease. So now let's visual representation of this plot, yeah? So this is the X1. If you just plot it, you can do it a scatter plot. So scatter plot of X and Y. This is how now. X10, Y15. X20, Y25. See, these are the dots. So you see this is a relation exists. Now coming to the thing of regression. So regression is somehow similar to the correlation, but there is a difference between there, and there is a difference application uh, uh, of the regression. What is simple linear regression? Regression analyzes the relationship between a dependent variable and one or more independent variables. Simple linear regression involves one independent variable and models the relationship as y is equal beta 0 plus beta 1x plus epsilon. So y is dependent variable, x is independent variable. Beta 0 is actually the intercept. What is intercept? Intercept where it cuts the y-axis. Beta 1 is the slope of the line, and epsilon is the error term. So this is a very perfect mathematical definition of regression. But now, whenever you're looking at it, so you then you will find it, understand it properly in 𝗏𝘆𝘁 without any problems. Now let's think something else. For example, um, we have an array. X is an array of X, which is the shape -1 and 1, and Y is an array of Y. So this is the X line of X, and this is the line of Y. So these are two arrays. We define that. Now we want to create a linear regression model for that, and this is how we want to put a model for that linear regression X versus Y. Now we want to understand the intercept. Model.intercept is, what is the intercept? If you use the model.intercept and then slope, which is the model.coefficient, this is how you will define that. Intercept is 5. What does it mean, 5? It means, look, here you cannot see it, but whenever this line is extended, then this line will cut the y-axis at 0.5. It means, what is intercept? Intercept is a way that if x is 0, how much will be the value of y? That's called intercept. So now we see that if x is 0, the y value will be 5. This is how a linear regression will look like. And why this is used for modeling, for the prediction. This is very interesting, that why it is used for the regression. Because if you have one value and there is a relationship existing, for example, you have this value and you have this value and you have this value, and then you defined that there is a relationship exists between these two values, between x and between y, and that's a positive relationship. And also you defined what is the coefficient of relationship there, and you define the intercept, and you define the slope of that line. Then you have the data to this point, then automatically you can predict this point, this point, this point, this point, all these data points which are not known to you, and you don't understand it, how much will be the value of this point. You don't know it, but you have only this this much data you have, but you want to know how much will be the value, for example, data if x is 40, for example. You will define, oh, that's 45. And all these predictions, you can do it based on this regression if you have understanding of intercept, slope, and all these things. So there is a bit confusion between correlation and between regression. You have to understand this, and this is very, very important. The correlation, you can tell me also that this is also a type of correlation. The same thing which we have here, yeah, it's also a type of correlation. Yeah, that is type of correlation. But now let's explore that why regression is a bit more important, and why its application is in a wider range. You can apply. So the purpose of correlation is actually measures the strength and direction of the linear relationship between two variables. It measures the strength, which is the coefficient, correlation coefficient, and direction, which is positive or negative, of a linear relationship, just linear relationship between two variables. And what is the regression? Regression actually models, it predicts the relationship between a dependent variable and one or more independent variables. So right now, if you have one independent variable, then you think that maybe that's correlation. But if you have 2, 3 variables, independent variables, for each of them, you can set up a regression. So this is how the difference between correlation is only between 2 variables, and regression is actually between not only 2, but maybe between 1 dependent and several independent variables. And you can define different those slopes and intercepts between those ones. Directionality, the correlation does not assume a causal relationship. Measures association. Causal, it means what was the cause of this relationship? Yeah. So it's not a cause. Yeah. So it's just, it assumes that this is association. These two variables are associated between each other. For example, these two are associated between each other, but it doesn't causation. It doesn't discuss the causation. Causation means because of this increase in X, this much increment in Y has happened. So this is not a foundational causation here, but regression employs a directional relationship from independent to dependent variable. Coefficient of correlation are ranged from -1 to 1, and regression coefficients, slope and intercept, describe the relationship. So for the regression, we don't have specific coefficient, correlation coefficient, but there we have slope and then we have intercept. Equation, no equation is involved for the regression. We have an equation of y as we discussed previously. This is a very simple linear regression. If you remember from mathematics algebra, this is the equation of line. Yeah? So just simple line, straight line equation is this one. Prediction. From correlation, you cannot predict something. From regression, you can predict something. Types. We have different correlation types here, but in regression, we have simple, linear, multiple linear, logistic, and polynomial regressions. We will be learning all these ones. Linearity, so measures linear relationships in Pearson correlation, while can model linear and non-linear relationships. This is the good thing about regression. And requirements of data. So two continuous variables are required in order to understand the correlation, while in regression, we just need only one dependent and one or more independent variables, which affects the dependent variable, prediction of dependent variable. So these are some explanations to differences between uh, um, between correlation and between the regression. So what is now, as you mentioned, that what is then the difference between linear regression and logistic regression? What does it mean? Um, in linear regression, um, the the my computer is a bit working slower, but still I'm trying. I already restarted that, but it didn't work. However, linear regression and logistic regression. So the linear regression is actually the response variable is numeric. So we have a response variable, and we have um, as we called it previously. So between a response variable and explanatory variables. So this response variable is actually that dependent variable, and explanatory variables are independent variables, as we discussed previously. It means that even if given values of explanatory variables, you can predict the values of response variables. So we have a response variable for which we are predicting something. For example, X, a response variable. Or for example, sales price. We have the sales data, for example, uh, for for 3 months, and we want to predict it for the month of fourth month and fifth month and sixth month. So how we can do that? So this sales price per month is actually, this is the dependent variable. So this is how you can understand and what are the other things. So response variable is dependent variable, and explanatory variables are independent variables. So linear regression is actually the response variable is numeric. It means, so this response variable that we are defining, what happened? These are from the previous lesson, so I didn't remove them because I didn't So response variable, for example, x or just y is usually that's the response variable. This is actually is equal to it is a numeric. For example, we are predicting a number actually. That's called response variable. But if you are predicting a category, uh, uh, or if your response variable is logical, if there is something logical there existing, then that's called logistic regression. And what is the difference between simple linear and logistic regression? There is only one explanatory variable within these ones existing. We will be coming to the understanding of between the um, linear regression and logistic regression. There is a difference between these two, but one is for the numeric values and another is for categorical variables. If you have categorical variable and you want to predict a categorical variable, then you have to use the logistic regression. And for the logistic regression, which is there is a logic they're calling it. For example, you have sales data, and then sales. If you want to predict exact number of sales, for example, you have sales data for 1 year and you want to predict the exact sales number for the second year. So that's called type of linear regression. Yeah. But if you have sales data for this year and you want to predict the sales data for the next year, that will it be increased or not increased? Then that's called logistic regression. It means so you have two variables, 0 and 1. Increased 1, not increased 0. So binary classification type of thing, which you can predict it with the logistic regression. This is how a bit difference between the logistic regression and between the uh, um, mm, between the linear regression. So now coming to the linear regression. So what is actually the linear regression? This straight line, which is defined by straight line, is actually defined uh, by uh, by very interesting thing. Now I will show you through uh, visualizations. Then that will be very easy for you to understand what is the intercept, what is the um, this is a number of claims, okay, and this is total payment. So we have data from a um, company, insurance company, and for that insurance company, there are a number of claims. For example, the different people they are claiming for the insurance of their cars, yeah. So, and this is the number of payments. So assume that these are the payments. So this is now in Swedish krona. So you can just assume that maybe it's in dollars or some whatever currency that you're thinking that's it. So these are the number of claims. We don't have this line actually. You see, we don't have this line. We have these dots. And we have these dots. Now, based on these dots, we draw this line. Yeah. So this you wanted to understand this relationship. Now this is the relationship that we have drawn here. This blue line. Good. We understand now the relationship that there is a relationship existing, and this relationship is actually a positive relationship. Because it's increasing, because if X is increased, this number of claims, number of payments are also increased. So this is how this relationship exists. Now, let's understand what is actually, if we are dealing this with as a linear regression. Now let's understand. We need for linear regression, the intercept. What is intercept? Intercept when X is 0, where the Y will be. Look at this. This line will be cutting the y-axis at this point. What do you think? How much will be this number?
5, maybe.
Uh, not exactly, but I think it would be around 20. See, because if you look at this is 100, this is 50. See, half of this 50 will be 25. This point, this is almost below 25, so around 20. So that would be 20 if you look at the calculations. Yeah, good. Now we need one more thing. We want to find the slope. How to understand the slope? We will another time we will take two dots or 2 points on the line and then understand the slope. So who remembers algebra and okay.
Slope is like the distance difference between the x and y, like from for example, the line point 1 until like the line point 2 is like um, the length of that two points are like 2 x and 1 y, so that's like 1.5 slope.
So for this line, can you calculate for me the slope for this line? What do you think? How much is the
This
difference
is, I think,
between x and
20, 50 maybe. Yeah, 50, because like we can see one exactly, because like the x and y um, distance is like increasing almost the same.
this slope? Yeah, these are 2 points, and then we just want to know the slope of this line. How you will calculate that? You will take the distance. Look at this. You should bring this line to this side and this side. Yeah. So how much is the increase from this line to this from this point to this point? What do you think? This is 40. This is 80. So it will be 40, 40 around 60, around 70. So this will be 70 increase on x side. Yeah. So from this point to this point, how much will be the increase on the y-axis? So it will be 150 to 400, around 250, yeah? So this will be 250 and this will be 70. So 250 by 70 is actually very simple calculation of slope. Did you got it?
Yes.
How you can calculate, yeah, visually the slope.
Yes, sir.
That's good. Now I will just show it to you visually, this one, and you will now have a proper understanding how you can calculate the slope. Look, these are two lines, yeah? This line, this dot and this point and this point. So increase, so this is the intersection of these 2 points, this point. So from x-axis to this point. So this is actually 70 uh, measures, because this is 40 and this is 80, this is 80, this is 100, yeah? And this is around 110. This is the middle of this one. So 110 minus 40, it's around 70. So this is 70 points increment in x-axis. And this is actually 250. If you divide that, that will be 3.5. The intercept is 20 and the slope is 3.5. This is how visually you can understand and estimate the slope between these two ones. Now, let's assume that we have another data set, and that's called, for example, different types of species that we have, for example, yeah. Let me find this data set and see if that data set is existing, and just let's insert that data set into our uh, connecting to a runtime to enable. Okay, now just, I think I have downloaded just this data set right now. This is the, oh, okay, that's, your warning is, thank you for that. Now, we want to insert what? We want to import atlas PD, then fishes will be pd.readcsv, and then we have to copy the path of file and paste it here. Oh, we have to put, see if it runs. It runs, that's good. Now look at fishes. What is fishes? It is actually species, type of species, and then mass gram of the that fish and the length of that fish. So we have actually value counts. We have how much? I really don't know. We have roach, perch, bream. So different types of this uh, 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 fish, of these species. So this is now coming another chapter that you have to understand that, and you have to see that, okay, we just need, for example, 4 species are there, yeah? So common breech, perch, for example, pike, different types of. Now just assume that, uh, let's visualize something from this data set. And how to visualize that? Oh, okay, I have to import matplotlib as pyplot, and I have to import Seaborn as well as SNS. And one more thing, no, one more thing that we can do, that we can use SNS dot this plot data will be equal to fishes, and x will be what? Will be the mass of in grams, yeah. So it will be the um, mass in gram. So this one, mass in gram, and the column will be the species. So like that. And what else we can add to this plot? Column wrap. Let's do it, for example, call equal to 2. And we can have bins as well. So just assume bins are equal 10, for example, equal to 10. And this will be this plot, not this plot. And pp dot, let's see what will happen. So we have 4 types of species. For example, bream species. This is how the histogram for that's actually working. See, we have 10 bins, and this is the different mass gram from the mass gram point of view of different species. So we have, I think, maximum of 25, and these are the different. This is another type of roach. This is another type of gram, mass gram. Another type of species. So this is the grams, the gram X, and this is the count of that specific species. Now look at this, for example. We have 0 to 250 grams, yeah? So even it's not not half kilo. and perch species type of fishes, and perch type of fish, for example. So look at this. Less than 100 grams is the highest having the highest numbers. For example, 25 rows or 25 rows within data points within this data set is actually is part of perch species of fishes, which is having mass gram of less than almost 100 grams. Look at, so it means small species there, yeah. So from mass point of view, from mass point of view, here we have between, if I look at this, 250, then 500 grams, which is half kilo, and then this is 1 kilo. Bream is type of species which is having heavy weights almost in comparison to others. And pike is also another roach. Roach is another type of species which is having the less grams weights there. So this is how you can understand that. Now let's do the summary statistics and then define something else. It means that in order to understand the summary statistics for this for these fishes, do something else like summary stats. It will be equal to fish dot not fish fishes dot group by species, but the aggregation will not be the mean, but it will be the mass gram dot mean. So let's run this one and see, for example, the average mass or the average weight of bream type of species or 670 grams, which is almost half kilo. The perch one is 382, pike is larger, heavier, and roach is 152. So these are the summary stats from these ones that we used. Now coming to the linear regression. So we can use a model for the linear regression, which is very important, and that's very playing a key role whenever you are working with the linear regressions. That's called a stats model. So from stats models, this is all the time you have to select stats models dot formula, from the formula of that dot API. This is how you can write it. Import OLS. This is the thing that you can ask that. Now coming to the modeling, we have to model that model math versus species, yeah. And just you can call OLS, and that will be mass gram and species. Data will be fishes, and just you should call fit that you have to fit this model. Now print what? Print summary of this model, yeah. Yeah, we can print summary as well, or we can print, first of all, let's print parameters of this model. Look at this now. If you're doing this, what was this? very simple data set. You have 4 types of species, and you have a column which is the mass, the weight of those species. And you want to know, you want to predict something. Yeah, you want to understand, you want to create a linear regression model, because you want to understand that, okay, if this species, how much, this type of specific species, how much will be the mass of it? Or you want to understand that, for example, if this is the mass of a species, what do you think in which type of a species it belongs? You got the point how regression models work? So intercept of this model is 617, the species 𝗵𝗃𝘃𝘃 minus 235, 𝗵𝗃𝘃 is actually 100, and these are the parameters of this model that you are having. Now, from previous slide, slide that we discussed, that we can model with or without intercept, for example. For example, if we want to model with intercept and and without intercept, so the different things that we can do with this modeling. And then we are coming to toward the fitting of the model. If you're asking, you're increasing here, for example, plus 0, I think that would be plus 0. So that will be without intercept, but right now we just model that with intercept. So this is how we did the modeling of this intercept. Now the coefficient are relative to the intercept. You know how you can define the coefficient that we want to know that this is relative to the intercept. Because when we have intercept and then we want to understand the coefficient, for example, for the perch side, yeah. So how you can define that? So you can just from 617 minus 235, 382. These are the coefficients, for example, in regard to the perch. This is how you can define. Or for example, for pike, 617 plus 100, so that will be 617 minus 465. That will be another coefficient for the for the um, for the for that specific type of species. So this was actually the stats model that you have to understand that, and how to call the stats model to bring it to the Python. Now let's do something else. For example, just see that, for example, we want to focus on BREEAM type of the modeling. Yeah, so just assume that we want to understand the BREEAM. Now, just how to do that? That will be fishes, where all the species equal to BREEAM. So we created a new data set where just only species are listed where they are equal to BREEAM. So these are all species equal to BREEAM. 34 of them are BREEAM type. Now let's do something else. Let's plot this one. See what is the mass and length of this specific type of BREEAM is there. For example, if SNS, we are using SNS, and let's use recplot. And for recplot, if you use x will be the length. This is the length. I'm just copying it because I don't want to make any mistakes whenever I'm typing it. Y will be the mass. Y will be the mass. Data will be the BREEM data set that we have extracted recently. And she will be none. This is the specific type of BREEM, which is type of fish. Length and mass. So you see there is a relationship existing between the length and the mass. Now let's run the model, yeah? And see what will happen. What was our model there previously we defined? This was our model previously we defined, yeah? This is the model. Okay, good. Copy that model. Paste it again. This is mass, not versus SPC, but versus length. Yeah. Instead of species, we can put length. This data is now changed to BREEM. The name of this model is also changed to length. Why? What happened? What's the problem? Model mass versus
Actually, math should be double S.
exactly. This is the problem. And both of them are wrong. Look at GPH. GPH. This is now the parameter of this model. Intercept is minus 1035. Length centimeters 54. So what does it mean actually? It means whenever the length is becoming this is becoming 0, so the intercept of mass will be minus. So this is how you can define the parameters of this model. Now coming to the explanatory values to predict. For example, we have explanatory data. Yes, we have set of data sets, and then we want to. I have a data, for example. I have a data set of explanatory data. What is explanatory data in this model? Who can tell me? We had explanatory data and we have responsive response variable, and we have explanatory variable. So from this model, which is explanatory variable and which is the response variable?
The response variable is mass in gram, and the explanatory variable is length in centimeter.
Brilliant. What does it mean?
It means mass in gram is an independent variable, and the length in centimeter is an independent variable that both of them are in linear regression model.
Brilliant. That's brilliant. Now let's generate something else. Let's generate explanatory data. And see what is explanatory data. Okay. This is a data frame we defined. Okay. Different types of lengths we defined. We defined 20 elements in an array. Between 20 to 40, this is the length of the array that we have defined, and we said, okay, we want to have not 40, let's include 40 there as well, so make it 41. This is the different lengths we have defined right now. What we want to do now, let's predict right now. How to predict it? We should print, and then the model that we have developed. This is the model that we have developed. See, this is our model. Copy, paste here, and then we should say predict for what? For explanatory data. What is this now? See, for each length which we defined new ones, it predicts a mass, specific mass in gram. So if length is 20, mass will be 55. Look at the visual. This is length, yeah, this is length. So 24, 26, 28. So you see there's a length is between 0, this is 0, and this is 38. So this is how the length is increasing, and this is how the mass is increasing. So based on this model, it says if the length is 20, the mass is 55 gram. If the length is 21 centimeter, mass is 110 grams. If the length is 30 centimeters, number 10, it will be 601 grams. 30 centimeter, this is 601 grams. Look at this. This is how you're assuming what we have done. In this model, actually, this is a very simple linear regression model. First of all, we defined that there is a relationship between length and between mass. Good. There is a relationship existing. Good. Now, if relationship existing, we changed that relationship into a model. This is how stats model works. We said, okay, now mass in gram and length in centimeters, these are the models that we want to use. Good. That's good. Now, I have different lengths. I have lengths which are not included in this. Look at 38 is included in this, yeah, in this model. But 40 is not included. 1146. So 40 is not included. Look at this. This you predicted 40. This will be the length of 40. Or you can just predict, for example, not 40, even 50, which is not there. Good. And do that. And these are the lengths. So if you have a length of fish, which is, for example, 50 centimeter, mass of that fish, if it's type of bream, will be around 1,637 grams, which more than 1.5 kilo. This is called linear regression, and this is how you can fit it into Python and predict something based on linear regression. This is called the linear. Now let's do something else with this data in order to make it very good. Let's don't increase it to 51. Just let's keep it to 41. That's not a problem, but you can do that. So this is what we have done a prediction for that. That's good. This is our prediction. I just want to keep it smaller, the data frame smaller. Now let's put explanatory data into a data frame. Okay, now we have explanatory data. It will be again our data frame pd dot data frame, and then coming to the yeah, so we have already that. Sorry, we have to have prediction data. Have to have prediction data. This is prediction data. Prediction data should be the explanatory data, which we have previously. Explanatory data, and then we should assign what there. We should assign mass gram. Mass gram is equal to model the result of this one. You will see what I'm doing it right now. I'm just creating a new data frame with the explanatory data and the prediction data together, all together. And that's it. Nothing else I do here. Special. So I just put these figures and these predictions together in one data set. That's it. I did this one. How I did this, I said, okay, this is explanatory data, which I had, and then assign a new column to it called mass gram. And then the value for this column will be equal to the result of this model. So this is the model. These are the results of this model will be the results of these columns. This is how we can put it there, and that's it. We create a new data frame. And why I created this data frame? Now let's see why I did this. If we just use SNS reg plot, and then we say, okay, X will be the length, centimeter, Y will be the mass in gram. I forget to put these ones here. And then data will be the data frame bream that we have created. This is one thing. Then I want to create a scatter plot. SNS scatter plot where the X will be the length, the Y will be the mass, but the data right now not will be the actual data, but the prediction data that we have predicted. Okay, and I want to see how much our prediction is accurate. Look at this one. So you see, these are and just put another thing. Yeah, and that's it. This is how the Rick plot shows. Rick plot. So these are the confidence intervals of this Rick plot. So this is the first plot that we have plotted here. This is another plot, scatter plot, that we have plotted here. So you see, predictions are not that much exactly the same as it was, as it is exactly the same, but it follows exactly the same intercept, the same slope, and the same coefficient. Maybe there are some points in the actual data set which are out of the, see, a bit different from this prediction. But still, they all follow the same thing. This is called how we predicted our data. So this is prediction toward the 20. This is prediction toward the 40, even more than that. See, this is all the predictions happen in different points based on the data that we have. This is how linear regression works, and it perfectly works. This is our understanding from the linear regression and understanding why we are using linear regression. So we had a data set, we had length of fishes, and we have mass of fishes. Now we develop a model which, if someone gives us any length of a fish, we can automatically predict that mass of that fish hold. Now, I hope you got this, and I hope you understand what was happening there. Okay, we will be having a 5 minutes break. If any questions, please ask me. Then we will be discussing the another topics. I cannot hear you in case if someone is asking me anything. Look, I cannot see your messages during whenever I am talking, because you see the time in another screen. If the screen was not clear, you could just, some of you just told me that I could just increase the but however, that's okay. Okay, any questions? Good. If no one is having any questions. Okay, for this model, I will add one more thing for you that you will understand that that you have understand that you have to know that. Look, this is the model. This is the summary of this model, but I don't want to put the summary for you here. Another very important residual of this model. Residual of this model, what does it mean by residual of this model? It's very important that you have to understand the residual. Now let's residual is, for example, 11. Residual is actually the definition of distance between the predicted and between the actual value. So this is actual value, for example. This is the data set, yeah? The length, just assume for this one, for example. Number 3. For number 3, if length is 23 centimeters, the mass will be 219. If 23 centimeters, for example, somewhere here, see? 22, 23, maybe somewhere here. So, for example, this way or this way. So these two dots. What does the residual means? Residual means the difference between the predicted value, which is the red dot, and the blue value, which is the actual dot. So it means how much the difference was between these two ones. We had a value actual point of data within the data set, and then we predicted something. And what was the difference between that? This is how, look, why it's below that. It means because predicted value is below the actual value. We had different, for example, for item number 13. Sorry, the predicted value is above the actual value. Now look at this point. This point. The predicted value is here and actual value is here. It's almost 233 points. There's a distance between the predicted value and between the actual value. So this is very important because you have to understand, and then at the end of that, you can get just calculate the mean value of residuals. So you see there are other values, 207. It means the predicted value is lower. This point, predicted value is lower, and the actual value is higher. 207 distance between these ones. This is called residuals. Then they can get the average of residuals and understand how the average of residuals work. That's very important whenever you are assessing the accuracy of model. I hope you got this one. Residual is actually the observed value minus the predicted value. So for this, we can just do that. You will see. If we see the mean of residuals, will be the NP dot mean of residuals. Yeah. So now print that one and see it is minus 7 point something. It's a very this is one of the it should be close to the zero. So whenever the mean value is much more closer to the zero, then that model is very accurate model. If it is very far away from the model, then that means the accuracy of the model is not satisfactory, and you have to put other ways to put it properly in hyper tune the model properly. This number is very close to the zero. You see this residual value that we have received, it's very close to the zero. So it means the model is very, yeah. I just want to mention to you intentionally that please don't pay attention to the -7 here. You have to pay attention also to E -13 here. So this is a very interesting number, and please, can someone write this to me in chat? How much is this value actually in usual digits as a float number? Or just can someone explain to me how much is this number?
Isn't this supposed to be almost zero, sir? Like it's either mean of residuals is always zero in terms of linear regression. So I would say this is an almost zero value.
Yeah, I just wanted to know, to understand your knowledge of interpreting the E -13. If such a number is, how much will be actually the exact mathematical understanding? I understand that this is very equal to zero. I just wanted to know actually if someone understands this number is actually -7, or this actually, or what is actually this number. But
So
however,
this number is
this is the number. Yeah, thank you.
E -13 means multiplying by 10 to power of minus 13.
This is the number. This number is equal to this number. So this is very, very equal to zero. So I just wanted to understand you that these are the notations, different types of notations, and you have to understand these notations. And this is not even, sorry, this is not, this is minus of this number. So this is now the number, this number, and it's very equal to zero. I just wanted to confirm that you got this concept. So this was the mean of residuals, and you have to understand how to the mean of the residuals are important whenever you are assessing the linear regression model. It means it's very close to the x and to the zero, and whenever it's the mean of residuals are close to the zero, it means that the model is very accurate. So this is how you have to keep all the time understanding of that. Now coming to the another understanding of logistic regression, another type of generalized linear model. Logistic regression is also a generalized type of regression, but it's used when the response variable is logical. Response variable is logical and then you have to understand this logic. And then from stats model, we used OLS. OLS was for the logistic regression, simple logistic regression. And for the logistic regression, we just use the logit function, and we have to understand the logistic model of those things. So this is how you have to understand the logistic regression. Now let's start with a data set, another data set, and understand if. Let me see if I can have that data set and bring it to you, and that would be good. So yeah, I have that one. Okay, so just let's bring it. Now we will be bringing this data set and as a bank data set. Okay. Bank data. But it will not be content on bank, or maybe not bank. Copy path. Copy path. So this is the data set. It means churned or not churned, in time since first purchase and time since last purchase. So this is a data set of the bank, and it shows us that if a client is churned or not churned. So what does it mean, churned and not churned? Who can tell me? Okay.
Are you asking, sir, what this churn means?
Yeah. So this client. So this is a data set here.
Yeah.
Has churned.
Yeah, churn in business sector, it refers to how many customers have stopped using your product or has ended your relationship with your business within a
Exactly.
specific given period of time, sir.
Exactly. Churned has churned. It means they just closed their accounts. They are not using the bank anymore. So they are not customers of the bank anymore. Not churned, it means still they are customer of the bank. So this is how the difference is there. Churned means what? So this is a simple data set. Has churned. Has churned has two values. 0, 1. 0, not churned. 1, yes. 0, no. 1, yes. So this is the difference between these two ones. So as I mentioned previously, if you remember, yeah, that whenever we have a logical explanation to something, if we have a binary outcome for something, yes, no outcome for something, doing, not doing, good, bad, so such type of outcomes for a model, then instead of a regression model, we have to use logistic regression model. So that instead of linear regression model, we have to use logistic regression model. You got the point? So this is how the difference between the regression linear model and linear logistic regression model. So this is a very simple data set. For example, this is time since first purchase, for example. This is time. And this is time since last purchase. So this is last purchase and how much time has been passed away. So this is the explanation, specific explanation. So between these purchasing or not purchasing. So this shows, this time actually shows the length of relationship. Yeah. So actually length of relationship is how much, and the time since last purchase is actually the recency of our activity. So how much time has passed that they lastly purchase something. So this is how, and this is actually the response, churned or not churned. So this is a very simple data set, and then we will be exploring some things of this data set. Now let's fit a very simple linear regression model for this data set. Okay, let's do call it, for example, model of what? Model of churn versus recency. Yeah. And this model will be linear model, and then we will understand how to do that. For the linear model, which function we should call from stats model? OLS. OLS is the function that we just, for the OLS, we have to use two columns. One is has churned, this column, and which another column will be? Time since last purchase. This is time since last purchase. And the data will be bank data, and fit. So let's see what will happen. Incomplete input. Thank you. Okay. Now what is this? The intercept is 0.49, which is 0.5 actually, and the time since last purchase is 0.06. So this is the time zero. So this is the parameters whenever we are fitting a linear regression model for that. So that will be the intercept, and then it will be the slope. So the intercept and the slope will be from the parameters of this model. Now let's define this intercept and slope here. Slope and intercept. So intercept, slope will be this is how we defined the new thing, yeah? So that will be the intercept and slope. That will be the parameters of this model. Now let's visualize this one through SNS scatter plot. And what will be the scatter plot? X will be time since last purchase. X will be time since last purchase. And what will be the Y? Y will be has churned. Y will be has churned. Now data will be bank data. Now also let's draw another line on it. We call it AX line. What will be that line? That line will be XY1 will be 0, and then intercept from 0 till intercept of that specific model, and then slope of that will be the actual slope that we defined. PLT dot show. Then let's have a look at this chart. This is the scatter plot, time since last purchase. So this is time since last purchase. See? Time since last purchase. This is has churned or not churned. We have in this logistic regression, look at this other plots. This is a linear regression, yeah? We have different values because we have continuous values here. We have different values here, numeric values. But in logistic regression, we will be having a very ugly scatter plot. Why? Because on the y-axis, we will be having only two values, either 0, either 1. Yes, no, because that's a Boolean, a logical response to that. And these are the numbers on x-axis, explanatory variables. So this is the response variable or target variable, for example. Now, what is this line? This line is actually the intercept and slope line. So we just we tried to fit a linear regression into such a scatter plot. Can you see something here? Do you think that that's logical?
Yes, sir, it is logical.
So what will be the logic behind it? Do you think
Um,
that there is this specific straight line making any sense there?
Yes, sir. Because again, when a customer starts churning or has churned from a specific company, from a specific goods or service, they don't purchase anymore. So the time since they have last purchase is related to the time that they have churned from the service or the good that they are purchasing from a specific company or business.
So as
Well,
as the as the time passes, so the customers churned, I think, more. So the number of churned people, customers are increasing. So it means the bank has to bring some new strategy. Otherwise, the bank will affect.
Okay. Now, this is the major mistake which all data analysts are doing, actually. You're trying to find a logic that this linear line is actually a proper understanding of how churn versus time works. Whenever you're looking in such data, you first of all, you have to understand that either this relationship is linear or not linear. That's not the question. And you have to automatically think of these two. Whenever you're seeing such things, for example, 0 and 1, you say, is okay. What is the response variable here? The response variable is numerical or categorical here.
This is categorical.
Exactly. 0 and 1, it doesn't mean that that's not, yeah, they are numbers. They are numbers, but actually those are categorical. They just didn't put yes and no, as Chan, not Chan. So those are the categories. Instead of putting that and making it a very long response, they're just putting it all the time yes, no, 0, 1. This is a very common practice. But actually, the response variable here is a categorical variable. And whenever there is a categorical variable, and then you're trying to find a relationship of that categorical variable with other explanatory variables, which are time since last purchased or other times since last. So whenever you're trying to uh, compare that with that, so then simple linear regression model is not the solution for that. You have to find now another solution for this such type of model to predict. What will be the another solution for this to find and predict? That would be a simple logistical regression that you have to use. Whenever you have such type of plots, which are all numerical, this is also numerical and this is also numerical, then this is simple linear regression. But if you have one categorical variable and another is numerical variable, then you have to come back to the logistic regression. And so we developed this. Technically, this model that we have developed, it worked. We just developed something. And this is the model. It worked. It shows that there is a relationship existing. But still, in order to define a proper and appropriate model for this question, you have to come back to the logistic regression. And from that model that we previously worked, dot formula dot API, we should import now another model which is called logit. That's good. Now this is the same thing, that we have to have a model churn versus recency, but not linear model that we have here. Linear model, you have to put it to the logistic regression model. Logistic regression, instead of OLS, you have to call logistic regression, and then has churned, and then time since last purchase, and then the data will be the bank data. Then we will be fitting this model, and then we will be printing the model parameters. Now optimization terminated successfully. Current function value is 0.683, and intercept is actually minus 0.35, and time since last purchase was 0. Look, there's a huge difference whenever you are doing this type of logistic regression and linear regression. Look at the linear regression. In the linear regression, it says the intercept is plus, while whenever you're doing a logistic regression, it says that it's a negative value. Time since last purchase is 0.26, and it says 0.06. See, this is the difference between whenever you are developing a logistic regression or a linear regression. Now you have to understand how to, let's visualize this one. Yeah, so let's visualize the reg plot. So if we have SNS dot reg plot, which is this regression plot, it's specifically for regression plot, x value will be time since the last purchase, and y will be actually the has churned or not churned, has churned, yes or no. The data will be actually the bank data, and the chi will be none, while now logistic will be true. Okay, just plot this one. This is now, do you think this is a straight line? See, this is not a straight line. So I visualize this one again here on this chart. On this chart, this is straight line, while this actual functionality of the regression plot, if this is a logistic regression, that is actually a curved shape line. So that's not a straight line. So this is the difference between the logistic regression and between the linear regression. For the linear regression, the line all the time is straight line, while for the linear regression, the line is actually, for the logistic regression, the line is actually curved line. Now let's do something else for this one. Do 𝗘𝗃 dot x limit -10 and 10, and 𝗘𝗃 y limit -0.2 minus 0.2 to 1.2 𝗘𝗃 dot see what will happen. So this is a zoom out of this line that you should understand the full thing here, that this is just a straight line, while this is not a straight line. This is just a curved line. We can do this zoom out also larger and larger in order to understand that how there is a difference between the curved line and between the straight line. This was just to show you that this line is all the time straight line, which doesn't actually represent the logistic regression here, while this is the curved line, and this curved line actually represents the logistic regression here. So this was the understanding of logistic regression. Now, that's it. Now, let's make some predictions. We will be removing this line. Again, I don't need this line. I just put it like that. This is just a simple linear logistic regression model with the curved line and two categorical variables. Now let's do some predictions. For example, if you want to have a model for recency, what will be the specification of that model for recency? That will be a logistic regression model where we should understand if as trend and time since last purchase. Time since last purchase. Data will be the bank data. This is a model that is already fit. Now, do something else for it. We have explanatory data. For that explanatory data, we have to create a PD dot data frame as we did for the previous one. And then time since last purchase. Let's define time since last purchase. Time since last purchase will be between -1, 6.25. The steps will be 0.25. So we generated another table of explanatory data. We want to predict for that explanatory data. Prediction data will be explanatory data dot assigned as trend Yeah. So this will be the not model recency as churned model. Yeah, model recency, predict explanatory data, prediction data. That would be our beautiful data frame. This is what we have done. We did a prediction. This is the prediction model.recency, which we have developed recently here. This is a logistic regression model. For that, you want to predict what? You want to predict all explanatory data. This is the explanatory data. What is explanatory data? We developed a data frame of different time period. So we have one. This is the data set that we have these times, yeah? These time since last purchase. These are the things which is within the data set. But we want to have another data frame like this, from -1 to 6.25, and each step will be 0.25. And we want to have this data set. And for this data set, we want to predict that if this much time is spent since last purchase, would the customer will churn or not churn? You got the point. What this actually means?
Yes.
Good.
So it's same as you did in for linear regression.
For linear regression. But the interesting point is here now, has churn is a very interesting value right now. See, it is not actually having a proper value of 0 and 1 because we are predicting. So for the prediction, this is because it's a logistic regression. You got it. So for the logistic regression, this is not just a linear regression, but to have a specific 0 or 1 there, because it's logistic regression in the curve is, and the line is a curved shape. So you will not be having a specific 0 and 1, but you will be having different types of numbers. And then you will decide, for example, if it is 0.8, it means sure that you are very much sure that it's 80% sure that it will be churned. Yeah. If it is 0.3, so you will actually 70% will be sure that not churned. You got the point in the calculation, the way that you have how you could predict. Look at this. This, if time since last purchase is 3.5, then it means 0.7%, 0.7. 0.7 is almost close to the 1. 1 is churned, yeah? Churned or not churned, yeah? So 1 is churned, yes, churned. So it means 0.7. 0.7, it means 70% you're sure, or this model predicts that if a time spent 3.5 since last purchase, then it is churned. You got how you will predict this logistic regression. Now let's visualize it. This is a rig plot. Has churned, data, bank data, logistic is true, and then we have a scatter plot. X is time since last purchase, Y has churned, data is prediction data, and the color, the color will be in red. And plot this one. See, this is actually the exact way that how your model works. So this line is not a linear line, this is a curved line, and the predictions are all along this logistic regression line. So it means 3.5, it says that it's 0.7. So this way, look, 0.7. So this point actually means that this is zero, not churned, this is churned. That's your 70% close to churned. See how this prediction can be uh, uh, interpreted. Now let's do something else. A very interesting thing. So this is the exact data that how you can do that. But if you want to have a specific data that either it's churned or not churned, then do the prediction data and do something else for the prediction data. For the prediction data that we have explanatory data, is already there. Oh, just let me know what's prediction data. Has churned it already there. So has churned already there. Now for this prediction data, let's add another column. Most likely outcome. What is most likely outcome? It will be NP dot round all those values. Prediction data. As churned. Now that's a good thing. Now we just use the round off method here. See, in order to make it to become 0 and 1, yeah? So this is the possibility. This is the likeliness, yeah? Based on the percentages. For example, 80%, it's likely that it will be churned. It's 40% is likely to be churned, for example. This is how you can calculate the likeliness, yeah? But if you want to just a solid number of 1 and 0, just round off those numbers, and then you will receive another table, another column of 0 and 1. And instead of having the predictions along this line, you can just have predictions specific on the 0 and 1 column. So let's just plot it again. That will be, x will be time since, well, just instead of typing it again, let's copy this one. This is the thing that we should copy that. Then the scatter plot will be a bit different. Scatter plot will be time since last purchase, and y will be the most likely outcome. Y will be the most likely outcome. This one. And then run it. And now this will be the another type of charts, for example. For all these times since last purchase, you are predicting exactly, will it be churned, not churned, churned, not churned. See? Based on this is the data set. This is the likelihood. This is based on percentages. This is based on exactly 0 and 1. Did you got the one? Okay, now I will just share with you the last slide. For the linear regression, we had an accuracy check. What was that accuracy check, if you remember? Who can tell me? Okay, that was the mean of residuals. So one of the things that we did some check of residual checks. For the logistic regression, we are checking the odds ratios. What is odds ratio? Odds ratio is the probability of something happening divided by the probability that it doesn't happen. So this is how the one of the things in logistic regressions that you're using as a ratio, and that's important whenever you are measuring the performance of a logistic regression value. So this is how, for example, this prediction data, and you can add odds ratio for it. And what's odds ratio for that? It will be the prediction data. Prediction data where has churned, has churned, which is the probability of doing it, has churned, divided by 1 minus prediction data is churned. This is the odds ratio based on the formula. Now let's visualize it, because you will understand it properly if you visualize this odds ratio, and this will be just a line plot. SNS line plot where x will be the time since last purchase, and the y will be the odds ratio. The odd ratio. So I didn't put s there, so that's okay. Odd ratio, and the data will be the prediction data. And so this is a curve line. See, the same thing. That this is the curve line. It gives you the same thing, the same understanding. If time since last purchase is increasing, then the odds ratio is also increasing. Odds ratio is increasing. It means the result is becoming more closer to the one, to the churning. Yeah. So that was the one. This was the one. Yeah. So the churning. So if time since last purchase increase, so automatically the odds ratio also increases. And if increases, it means the result of prediction becomes closer to the one, which is the yes churned. Yeah, the results will be churned. This is how you can understand the difference between the from this is called logistic logarithmic scale as well. We will be discussing logarithmic scale totally different. What is logarithmic scale? Maybe lots of you now understand it and know it, but this is how where logarithmic scale has emerged from if someone's asked you from where it has been emerged. So this is the odds ratio, and this is the log of odds. So for the logarithmic value of the odds ratio, we have to define that as well. So this is the different things that we can predict and understand. So what does it mean? Odds ratio is R values easy to interpret in the odds ratio. That's but changes are not properly interpreted in this odds ratio. And also for the most likely outcome, so those table that we have there, these are the most likely outcomes. We can predict, but measuring is will be a bit difficult for us. So this is also a most likely outcome, which is very much understandable and predictable. This is how interpreting of different values of this logistic regression with different measures. This is how you have to understand the logistic regression. Now, for the one more thing, which we will be coming to it tomorrow, that will be the confusion matrix for the logistic regression and also the sensitivity. So these two ones we can discuss tomorrow. And whenever we have discussing it tomorrow, the logistic regression and sensitivity, the chapter of logistic regression will be completed, and this module will also be completed. So statistics probability has been completed, and now regression modeling will be completed. Then we will be going for the machine learning. Machine learning is our final model, and there I will try my best that besides logistic regression modeling, we will discuss other types of models, starting from very basic ones, decision trees, or for example, Kaizen models, all very basic ones. But we can also discuss the other types of complex models as well, just as an introduction to it. The point of machine learning is just introduction to machine learning in this advanced data analytics, because the job of data analysts are actually analyzing the data and generating a proper insight from the data. While also sometimes, whenever you're trying to predict an outcome for something, then that would be job of a data scientist actually because modeling and predictions and all those things. But because this model is advanced data analytics, we will be having a look at the prediction modeling as well. So any questions, please ask me. Sometimes it's getting a bit difficult. And I understand that's because complex technical things. But if you don't understand it, please feel free to all the time ask me or message me in the group. I will just reply to your queries and questions. If someone doesn't understand it in English, so please let me in other languages if you want to. I can explain it after this time. Our today's lesson has been concluded. Thank you for the participation. Any questions? I am at your disposal. Thank you. Okay, there is no questions. It means everyone is now perfectly understanding the regression modeling. I want to know how much of you have been completed the 𝗗𝗃𝗃 certification. I just received 24 of you that have been completed the 𝗗𝗃 certification. Is it difficult? Is it something that you don't understand? Are you hesitant to ask specific technical questions? So what is the problem?
Yeah, sir. I just want to say I have completed the Kaggle database course, but I wanted to ask if same question with Ali. Can we have your collab notebook on foundation of statistics so that we can recall the lessons that we've had regarding statistics?
Yeah, sure. As you see that I'm just trying to find the time to do all the things that you're asking, and during my Saturdays and Sundays and weekends, and during the week I'm also working 2 shifts, but that's okay. I will, as I did in data visualization, if you go to the classroom, and then you will see that all the materials perfectly included to you for the data visualization, for the Python. So everything is there. So similarly, we will be putting all the data for the statistics there as well.
Thank you
But
so much,
there is
sir.
a sequence there as well, because regression is part of that model. So let me finish this regression as well, because you see that there's one Colab notebook from my side, because regression is actually the continuation of that model. So if when it's completed, all the videos, materials, resources, everything will be uploaded to the classroom. No worries about it.
Understood, sir. Yeah,
Yes.
thank you so much. Really appreciate it, sir.
Okay, thank you for the participations. شما رو به الله میسپارم. الله حافظ شما. وقت خوش.